Today we're going to talk about non-Mendelian genetics. Sometimes it's called complex inheritance, and really it is just talking about genes that don't follow a straight dominant recessive pattern. So we're going to go through several of those. To start, we will remember that Mendel's laws are the law of dominance, some alleles being dominant, so winning over recessive alleles, the law of segregation. So law of segregation is that we inherit two copies of each gene, one from mom, one from dad. And the law of independent assortment is that those don't go together. So today we're going to start talking about in the times when we don't follow those laws. All of these things still do follow the chromosome theory of inheritance, though. All genes are located on chromosomes, and the behavior of those chromosomes during meiosis accounts for the inheritance pattern. That is Mendelian genetics and non-Mendelian genetics alike. No matter what type of inheritance, you are following the chromosomal theory of inheritance. Okay, so exceptions to Mendelian laws or to Mendel's laws would include incomplete dominance, codominance, multiple alleles, and polygenic traits. We're going to go through those one at a time. So let's start with incomplete dominance. So incomplete dominance is exactly what it sounds like. It's when if you cross two opposites, like a red that we're seeing here and a white, instead of having red dominate over white or white dominate over red, you end up with something in between. So a heterozygote gives you an in-between phenotype. So this would be red and this would be white. So if I cross a red and white and I get an RW, then I get a pink flower. So let's do a practice problem with that. Oh, I'm sorry, got ahead of myself. So this would be another example of incomplete dominance in nature. So here, this is the straight allele. This is the frazzled allele. And if you are heterozygous, you end up with frizzled feathers. I think these guys are absolutely fabulous. I probably have a hard time seeing. All right, so let's do an example with incomplete dominance. In humans, curly hair is incompletely dominant to straight hair. Somebody mentioned that the other day when we were talking about hair. So the heterozygous individual has wavy hair, right? So you end up with something in between. So let's cross two people with wavy hair. So if they have wavy hair, then they have to have one of each. So they have a straight and they have a wavy. So notice here, guys, that we're using this little apostrophe to show the opposite trait because it's not that one is dominant to the other. You could also show it with a completely different letter. You'll see it both ways. So let's cross our two people with wavy hair. So they each have one of each. This is my curly, the plain H, and this is my straight, the H with the apostrophe, and the other parent also is wavy. So we're going to do the same thing. So when we combine them, this baby would have two curlies. This baby would have one of each. This baby would have one of each. And this baby would have two of the straights, right? So that makes this baby curly, this baby wavy, because they have one of each, this baby wavy, and this baby straight. So when I cross two heterozygotes for an incomplete dominant, I end up with a 1:2:1 ratio, right? And then my phenotype ratio is also 1:2:1. So notice that with incomplete dominant traits, our genotype ratio and our phenotype ratio are exactly the same. Let's do another one. So here we have curly and straight hair again. So this time the mother has wavy hair and the father has curly hair. Okay, so take a second and pause the video and write down what the cross is. Create your Punnett square, see if you're set. Okay, so mom has wavy hair, so that means she has to have one of each. She has to be heterozygous to be wavy. And dad has curly hair, which means he has two of these curly alleles, which we show with a plain H. So when we go ahead and cross mom and dad, this egg and the sperm give me two curlies. This one gives me a curly and a straight, so this baby will be wavy. This one, since it's the same thing, is going to give me two curlies, and this is going to give me a curly and a straight. And here, just like we were doing before, notice that I could have just done one and got exactly the same thing because our dad could only give us the curly allele, right? So here, my genotype ratio is 1 to 1 to 0. And my phenotype ratio is also 1 to 1 to 0. Again, look, see that my genotype ratio, my phenotype ratio are the same. I have one that is homozygous, capital H, curly. I have one that is heterozygous, and I don't have any homozygous straight. So that is how I get my genotype and phenotype ratio. Let's do one more. Again, pause the video and try to do it on your own. So here we have flowers that are red if they have the plain R. They are blue if they have the R with apostrophe, and purple if they have one of each. You guys know if you mix red and blue, you get purple. Okay, so what happens if we cross a blue rose with a purple rose? So we already said that blue is homozygous for blue, right? And purple has one of each. So I would do that. And again, you could totally do another one of these all the way down. You'll get exactly the same answer. That's not wrong. Okay, so if I go and I combine, this one will be purple because I have one of each. And this one will be blue because I have two blue alleles. So I am going to have a 0 of my plain R's to 1 of my heterozygotes to 1 of the homozygous for blue. And that will be the same for my phenotype ratio because this one is going to be purple and this one is going to be blue.